Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by Edupedia World. The previous lecture we discussed about hardness. We saw the different methods by which we measure hardness of a body. Before that we had discussed about the tensile properties, the stress-strain relation. Today we'll see another type of mechanical property that needs to be discussed, that is fatigue. As we had discussed in the introductory lecture, that fatigue is the type of failure which occurs under fluctuating stress. So fatigue is basically failure when there is continuously varying stress, also called as dynamic fluctuating stress, right? Since the stress is dynamic and fluctuating, what happens is that instead of the failure occurring in ranges of UTS, that is ultimate tensile strength, the failure actually occurs at much lower stress levels. In fact, it can occur even lower than yield stress level. So if you remember the stress strain curve, the engineering stress strain curve, this was stress, this was strain. We had something like this where the failure occurred here. This was the UTS, and somewhere over here was yield strength. So what we are telling about fatigue is that the failure will occur at much lower stress than yield strength or ultimate tensile strength. That is, if there is a fluctuating load even of this stress level, then the failure might occur. We'll see the details of when a failure can occur at a given stress level, when a failure cannot occur at a given stress level. But the take home till now is that for fatigue, failure can occur at much lower stresses than ultimate tensile strength or even than yield strength. Okay, now for fatigue to occur, normally what happens is that lengthy period of repeated stress is required. I said that we have fluctuating stress, but normally the number of fluctuations of the stress that is required for fatigue to occur is very high. Now fatigue is one of the most common reasons for failure of structural material. In fact, this is the most common reason for failure apart from corrosion. Corrosion is primary reason for most of the failures, but apart from that, fatigue is the reason for most failures, because most of the machineries, if you think about, are in constant fluctuating stress condition. For example, let's imagine the wings of an airplane. When the airplane is moving in air, the wings are in continuous fluctuating stress. Why? Because there is a lot of air friction going on and stuff. Then talking about bridges have a lot of fluctuating stress going on because the vehicles are continuously moving, which causes changing stress scenario throughout the bridge, right? And fatigue as such is a catastrophic, insidious and brittle like failure. What do I mean by this? Catastrophic means the failure occurs really suddenly. Insidious, again, it occurs from within the material and is quite difficult to see from outside before the failure actually occurs. And brittle like, we'll see that the surface finish of a fractured material due to fatigue has a brittle like nature. What this means is that fatigue is not only one of the most prominent reason for failure, this is also one of the reasons which can be very disastrous, because you might not be knowing that a material is going to fail. There may not be any previous indications of any internal damage within the body. In case of tensile kind of failure, the material actually has some plastic deformation going inside it, which can be externally visibly seen that there is some changes going on. But if there is no plastic deformation, as can occur in the case of fatigue, then you do not have any indication that the material is actually weakening from inside. Therefore, it can be catastrophic, and for that same reason, it is very important to know what is the fatigue life of a given material which is used for a structural application, so that we can predict from beforehand that how long will the material be working properly and when do maintenance work need to be done on the material in order to avoid such catastrophic failure due to fatigue happening within the material. Okay, this is one of the reasons that we need to understand. Now, we have said that fatigue occurs in cyclic loading circumstances. Now, what are the different possible kind of cyclic loading that can take place? If you think about it, cyclic loading can be what is known as reversed stress cycle. It can be what is known as repeated stress cycle or random stress cycle. I will discuss each of them so that you know what are the possible stress scenarios that can occur. In reverse stress cycle, what happens is that the fluctuating stress is periodic in nature and the mean value of the stress is 0. So it is mirror like. This is 0, sigma max, sigma mean, and sigma mean is just negative of sigma max. Okay, so it is just reverse. This and this region is equal. This is reverse stress cycle. Then we have repeated stress cycle, which is again sinusoidal in nature, but the mean is not 0. Okay, so this will behave something like this. Fine, this will be something like this. So now sigma max and sigma mean are not equal in magnitude. Sigma mean is somewhere over here, so the magnitude is only this much, whereas sigma max is here, the magnitude is much larger. And the mean value, this is sigma m, the sigma mean value, mean stress is not equal to 0. This is not equal to 0. So that is repeated stress cycle. And random stress cycle is basically a stress cycle where there is no particular pattern to the stress behavior. So something like this. There is no prescribed pattern to the behavior. That we know that what are the different type of cyclic stresses that can occur in a body, let us understand some terminologies associated with the cyclic stresses. The first thing is known as mean stress. Mean stress is basically the average stress which can be found out by sigma max plus sigma mean upon 2. So this is my mean stress. For reverse stress cycle, the mean stress is 0. For repeated stress cycle, the mean stress is not equal to 0. Range of stress is basically the range of stress is this whole length, the difference between maximum and minimum, sigma max minus sigma mean. This is the range of stress. Okay, stress amplitude is the amplitude of stress. So the amplitude of stress will be range of stress upon 2, or sigma max minus sigma mean upon 2. That is stress amplitude. Okay, and stress ratio, finally, stress ratio is the ratio of sigma max, rather sigma mean over sigma max. That is the stress ratio. What is the minimum stress during the cycle to what is the maximum stress during the cycle. For the reverse stress cycle, the stress ratio will be equal to -1, because sigma mean is minus sigma max, that is -1. Okay, now one point to note is that it might even so happen that the sigma mean is also actually positive stress. That is, if the 0 is here, it does not mean that the minimum stress should be less than 0. It can so happen that the minimum stress is also actually more than 0. Fine. We understand what are the different type of cyclic loading that can occur, which can lead to fatigue. Next up, let us see something important. This is known as a SN curve. A SN curve is basically a curve which plots the number of cycles required for failure at a given stress amplitude. Okay, so what this does is it plots number of cycles for a failure to occur in the material at any stress. What we see here is that we have two types of materials. One is A and the other is B, let's say. The A type of material, the B type of material has, with increasing number of cycles, the stress amplitude, the minimum stress amplitude required keeps on decreasing. What I mean is that for 10 to the power 5 cycles failure, the stress amplitude was somewhere over here, right? Over here. Whereas for 10 to the power 7 cycles, the failure can occur at a lower load. Okay? Alternatively, what we can say is for material type B, if we have lower stress amplitude, then the number of cycles to failure will increase. If we have higher stress amplitude on the body, then the number of cycles to failure will decrease. Fine? And this keeps on decreasing, this keeps on going, and finally it will saturate out at very very large number of cycles. And these values are already very large. 10 to the power 9 is basically 1 billion cycles, right? So that's that's a large number of cycles taking place. Whereas the material type A that we see here, what we see is that beyond a certain stress level, below a certain stress level, how much so ever we increase the number of cycles, fatigue failure will not occur. So there are certain type of material which has what is known as endurance limit. Endurance limit means the stress level below which fatigue failure cannot occur, how much so ever high the number of cycles be. Now you might ask that what are the type of materials which fall under A category and what are the type of material which falls under the B category. The A type of material are basically the iron based materials. B are mostly other alloys like aluminium, copper, those things. So iron and also titanium, this are shown to have an endurance limit, also alternatively known as fatigue limit. Fatigue limit. So such materials will have a limit, a minimum stress amplitude below which fatigue failure will not occur. So this is actually a good thing. This is actually a good thing, because if we know that a material has a fatigue limit, that is a minimum stress amplitude below which it cannot fail, then we will design the material, we will design the component such that the stress amplitude on the body remains below the fatigue limit. Thereby we are safe from fatigue being occurring. We will never have a fatigue failure in the component. But materials which do not have fatigue limit, we do not have that option. We need to keep monitoring the status of the component. Also we need to do studies and find out how many number of cycles the material is safe to operate till. Okay, this essentially kind of gives you an idea about the number of cycles a component should be exposed to before it needs some maintenance or it needs to be changed. Now the tricky part is that though we have shown here this as a single line, this is not a single line. The SN curve, it does not mean that all the components which belong to material B and which has, let's say, this stress level will fail at 10 to the power 7 number of cycles itself. It may so happen that one of them breaks at 10 to the power 6. It may so happen that one of them fails due to fatigue at 10 to the power 8 and a third actually at 10 to the power 7 number of cycles. So what this does is, this is the averaged out number of cycles at which a large number of such samples failed, right? So instead of plotting a single line, what is more practical approach, what is more statistical treatment, let's say, is that we provide a probability range of failure like we have done here. What is done here is that this line says that anything below this here has a chance of survival of 99.99%. Okay, and anything beyond this is the best fit line, so this is the average line. Anything beyond this will be 90% safe, anything beyond this will be 99% safe. Similarly, we can plot a lot of lines and by using lot of data. So this is basically a statistical treatment, right? What this means is, if you have a stress level of 500 and if you have a body which has this distribution and we have already gone till this number of cycles, we can say that the material will even now be safe is 99.99% certain. If we have gone till this number of cycles, then we can say that the material will still be safe is only 99% certain. If we have gone till this, the safety is guaranteed only 90% of time. Till here, it is more like 50% of time. It's the best fit curve, more like a median value, right? So what this means is that the study of fatigue using experimental value is not an absolute thing. You cannot guarantee for certainty, but obviously you can make a probability statement that whether it is going to be stable for how many more cycles by how much probability. Fine. Now let us see the idea behind how does fatigue occur. What are the steps involved in fatigue? So the first thing that happens is there is a crack initiation. There is a region where the crack needs to start, where the failure begins, just begins. Okay, and the crack initiation more often than not takes place at places of stress concentration. What do I mean by stress concentration? Stress concentration are regions like scratches or edges where the value of stress is high. They are prone to be regions of crack generation. Like here in this example, this corner has been the origin for the crack generation, for the fatigue to begin. The next step is crack propagation. The failure which has started over here in the second stage propagates through the material, right? It propagates, and during the propagation we see what is known as beach marks. This is a standard mark which is a fingerprint of fatigue. Most of the fatigue failures you will see these type of marks, either beach marks or what you can see is known as striations. Okay, both will look similar. Some things can be seen under naked eye, something needs to be seen under the microscope. And finally, beyond a certain range, once it has reached a certain range, the material can no longer take the stress and the final failure occurs. And more often than not, the final failure is more of a brittle like failure. You can see the shiny surface over here, right? This is trademark brittle failures. So these are the steps involved in a fatigue failure. There is a initiation of crack, then the propagation of that leading to certain marks, and final failure occurring. So what are the factors that affect fatigue failure? We have already seen that in the SN curve, that higher the stress, lower will be the number of cycles required for fatigue failure. So that is there. But also the mean stress, there in the SN curve we used stress amplitude. Here we are talking about mean stress. If the mean stress increases, even that has some influence. What is the influence? With increase in mean stress, there's a decrease in fatigue life. So everything constant, if we have two stress scenarios, in one in which the mean stress is higher, then for that case the fatigue life will be shorter. Okay. The second most important factor for fatigue is surface effects. What do I mean by surface effects? Surface effects are the conditions on the surface which affects the fatigue scenario. So one thing is, what are the design? How is it designed? If there are stress concentration regions left in the surface, if there are edges, nooks, scratches, then that can lead to generation, or that can lead to the origin of the crack, right? And thereby the fatigue failure can start. So a good design can prevent fatigue failure, or at least it can slow down fatigue failure. Then again, there can be surface treatments, that is the surface can be treated and thereby fatigue chances can be reduced. What are the possible surface treatment? One is residual compressive stress. One of the methods is known as short pinning. By short pinning, what you do is that you generate a residual compressive stress within the initial few microns of the material, and that reduces the chances of fatigue. Compressive stress is good for the material. It reduces fatigue. Second possibility is case harden the material surface. By case hardening, we mean either carburizing, carbonitriding, nitriding, those kind of things, which generates a thin surface layer which is really hard, and thereby crack initiation becomes quite difficult, and as a result the fatigue slows down. The process of fatigue takes a longer time to occur. Okay, so now just to recap the whole lecture, what we have seen is, we started by discussing what is fatigue. We saw the different type of cyclic stresses that can lead to fatigue. We discussed about the SN curve, the endurance limit, two type of materials, one which has a endurance limit or fatigue limit and one which does not have. We understood that the SN curve is actually a probability curve rather than an absolute curve. We understood the different steps involved in fatigue: crack initiation, crack propagation, and ultimate failure. Then we saw the different factors affecting fatigue in addition to the stress amplitude. The factors were mean stress and different surface effects. With this, I'll conclude the lecture on fatigue. Fatigue in itself is a very large topic, similar to all the different topics we are discussing here, and each of this topic can actually go for 8 to 10 hours lecture. So these lectures are very basic introductory lectures, just to give you a glimpse about the different kind of mechanical properties and mechanical behaviors that a material show. Next lecture, what we'll do is we'll discuss about creep. Creep is basically the behavior at high temperature. So hope you are here for the next lecture. Till the next lecture, have a great day. Goodbye.